if you can avoid it. So I'm going to stick with just ordinary integers. For example, like -3, 0, and +3. 0 is always a favorite number in making up tables of value. If I enter the value of x as -3 in the first equation, you can then find what y would equal. And that sets up an ordered pair. Now, if -3 is x, then -3 on this side becomes +3, and y is 6. This is the value for x, and this is the value for y. You can see that such a pair of numbers can be plotted on the graph. In other words, if we have -3 for x and +6 for y, the location of that point is right there. On graph paper, you would find that point exactly. I will write its coordinates, -3, 6 for that point. Now, continuing, if x is equal to 0, you can see that y is 3, and once again we have a pair of numbers, one for x and one for y. We can think of those as an ordered pair and graph the point representing it. 0, 3, well, it simply means that you don't go left or right on the x-axis. You stay at 0 and go up 3 units. And here is then the point 0, 3. That's enough points to determine where that line should go. A straight line only requires 2 points to see where a line should be drawn. But we always work out a third point to make sure that all 3 points are lined up. If you've made an error, you can obviously see that that is the case, because the points will not be lined up. So if x is 3 now, and you solve for y, subtract 3 on this side, you end up with 0, and so 3, 0 are the values for x and y. Putting this on the graph, x is equal to 3, so we go 1, 2, 3. Y is 0, which means you don't go up nor down, and that therefore is the point, and we'll write its label, I suppose we can refer to it as, or its coordinates, 3, 0. Now, as I explained, these points are lined up. And what it means is that if you draw a line through those points, you'll get the line that represents the equation x plus y equals 3. So that line is the line for x plus y equals 3. We either actually write the equation of the line beside the line, or we can just reference it by using the line number. We would do the same sort of thing with the other equation. You must do this twice, you see. Let's draw the table of values over here where we have room, and we set up a box arrangement like that with a line through the middle, and this is the x row and this is the y row. Divide it into 3 boxes and choose numbers for x, any number that you want to. And one other point, if you're when you're choosing these numbers, always write the smallest number first, the next size number up next, and then the largest number third. Don't mix up the choices for x. Not that you couldn't do it and still get what you wanted, it's just that it seems more organized this way. We'll pick any number that we want to, such as, let's take, well, how about negative 4, 0, 4. In the second equation then, I'll put the 2 beside this table, so that, and if we put negative 4 here where x is, negative 4 over here becomes positive 4, so we end up with 5. Negative y equals positive 5, therefore positive y equals negative 5, and negative 5 will go in that position. The position of that point would be, if you went to the left, negative 4 places, and down here, negative 5 places. On your graph paper, you would have that grid point, and that is negative 4, comma, negative 5. For 0, if x is 0, then you have minus y equal to 1, or y equal to negative 1. 0, negative 1 is over here. 0, negative 1. And finally, if x is 4, we end up with 1 minus 4 on the right, which is minus 3. Minus y equals minus 3, or y equals positive 3. So 4 comma 3 is located here for 4 and up here for 3. 4 comma 3. Check to see if the points are along a straight line. On graph paper, you will find that they are. And so, draw a straight line through these points. And that line then represents equation 2. And so let's label it by writing the equation that it represents, x minus y equals 1, or label it as I did the other one by writing its number in brackets like that. You can see that these points intersect at a single point located there. Now, that point there is 2 over this way and 1 up this way. Let's write its label, 2 comma 1. In other words, that then represents the solution to the system. 2 comma 1 is the root of the equation, and it's been solved by the method of graphing. I'm going to explain how different kinds of solutions are possible. There are cases where problems result in the equations producing lines which are parallel. So I want to show you how we treat those cases. Let's assume that that is a line represented by an equation, and that this second line represents the other equation, and they're exactly parallel. At least I've tried to draw them parallel. We'll assume that they are. This is a system of equations, but there is no intersection, and there will never be an intersection, no matter how far these lines are produced. Now, such a system, whenever you're given one like it, you will simply say in your exercise that there is no solution and the system is inconsistent. We want you to learn that term. Such a system is inconsistent. No solution is possible since there is no way those lines will intersect. On the other hand, if you have a pair of lines in the system where one equation produces a line such as that, And the second equation produces another line, but also in the same place. Now that single line drawn on the board represents two equations actually, where the lines coincide. Now, every point along that line is a solution to the system. In other words, we have an infinite set of points which can be used to solve the system. So we refer to these types of systems as dependent. I want you to learn this word dependent. You have an infinite number of points that are solutions. You have already experienced systems that intersect, and of course, to complete our study of different kinds of systems resulting in different kinds of solutions, I will draw that one down here too for the sake of completion. Here you have what is referred to as an independent and consistent, or the other way around, consistent and independent. Doesn't make any difference. This is consistent and independent. These are words we use to identify the different situations. So there it is, and this has a unique or single solution. I have classified systems looking at graphs of lines. This time I want to show you how we can classify systems by looking at the coefficients of the variables and the constants of a given equation. It's somewhat of an algebraic solution regarding the classification of systems that I want to deal with now. Suppose we are given the following. Let me algebraically. And here are the equations I want to look at. Ax plus by equals c, 1. Dx plus ey equals f. A, B, C, and D, E, F are numbers, or, as I've referred to them before, are parameters. Let's write that. A, B, C, D, E, F are parametric values, or simply parameters. That means that you have to think of those parts as carrying numbers. Now, if we're given this situation that A over D, that ratio of numbers, is equal to B over E, the coefficient B divided by E. If these two are equal to each other, for example, if this A was a 1 and D was a 2, B was a, say, 6 and E was a 12, these ratios equal to the ratio of constants C over F. These are not the same. This system is being inconsistent. Let's look at the other. If we have coefficients A over D equal to the coefficients B over E, but this time C over F equals the other ratios, this is where on the graph the two equations would have lines that are drawn one on top of the other, or the lines would coincide, and the number of solutions is infinite. Now, if you have A over D not equal to B over E. As long as those ratios are not equal to each other, you will end up with a unique solution and consequently is classified as a consistent and independent system. The next method of solution is by determinants. I will explain what a determinant is first. A 2 by 2 determinant is an arrangement of 4 numbers in a square pattern. Such as 7, -3, 5, and 2. We place vertical lines around this square arrangement of 4 numbers. There are several symbols for determinants in use in mathematics literature. They are, first of all, the one that you now are looking at. Another symbol that we can use for determinant is simply the letters D, E, T, and some letter like capital A to refer to the square arrangement of 4 numbers. Another symbol that we can use to refer to determinants is a delta symbol, delta A, where A refers to the square arrangement of numbers. In other words, we can say that A is the square arrangement of numbers 7 minus 3, 5, 2, using round brackets like you see. Now, delta A is a number. In other words, the determinant of a 2 by 2 arrangement, square arrangement of numbers, is an actual number. And that number is determined in this way. You take 7 and multiply it by 2 along the diagonal that way. And subtract the product of the numbers taken along the diagonal in the other way. You subtract 5 multiplied by -3. That's sometimes called a diagonal product. And this other, the off-diagonal product. And they must be subtracted. Take the diagonal product and subtract the off-diagonal product. That produces a number. So a determinant is a number. And in this case, the answer is 7 times 2 is 14 minus the -15, 5 times -3, for a total of 29. Let us generalize this by using symbols instead of numbers. In other words, that if I take a number, call it A subscript 1, followed by B and A subscript 2 down here, followed by B subscript 2 there. If I put vertical lines around them like that, there is a determinant. And the determinant is always equal to the diagonal product A1, B2 subtracted by the off-diagonal product A2, B1, or B sub 1. Memorize that. Here are a few more examples. Three, 6, 2, 1. This is equal to 3 times 1, subtract 2 times 6. This is equal to 3 minus 12, and the answer is minus 9. Minus 4 minus 1, 2, 6. Minus 4 multiplied by 6, subtract negative 1 by 2. This is equal to negative 24, positive 2, and that is equal to negative 22. I will now demonstrate how a 2 by 2 system of equations can be solved by using determinants. This is a method suggested by G. Kramer, a mathematician of the 18th century who used determinants to solve systems of equations. It is fairly efficient for up to a 3 by 3 system, but beyond that it requires too much effort due to the enormous amount of calculations required. The first step is to make sure the terms are in the proper order in preparation of the solution. That is, you must have the x terms one underneath the other, followed by the y terms underneath the other, and finally the equal sign followed by the constants. Let's take an example such as 2x minus 3y equals 4. I'll leave the x out for the time being and put it in another color. Similarly for the y. So we have 2x minus 3y equal to 4. That's equation 1. Then we'll have 5x plus 2y equal to 1, and that'll be our equation 2. So now this is, of course, 2x minus 3y, and this is 5x plus 2y. We want to do the following. Let delta C represent the determinant of the coefficients of the variables x and y. Let delta C represent the coefficients of the variables x and y. You see the numbers 2, minus 3, 5, and plus 2 form a 4-number square arrangement of numbers. Let's pick them out, ignoring the x's and y's. That's why I wrote them in different color, to concentrate only on the numbers in black. So delta C will therefore be equal to 2 minus 3, 5, 2. Now we know that this has a value. This is therefore a determinant. Now it has a value. Its value is 2 multiplied by 2, subtract 5 multiplied by minus 3. Completing the solution, the answer is 4 plus 15 for a total of 19. From delta C, take out the x column of values and replace it by the constants. It's very important that you follow this instruction, and I will repeat it. From delta C, take out the x column of numbers, which is 2 and 5. Those are the x value, coefficients of x, and replace that column with the constants. What we have then is a square array that'll look like this. 4 will go there, and 1 there, followed by minus 3 and 2. That's all that we do is take out the x column of numbers out of delta C and replace it with the constants. I will call this delta x because it was the x column that I took out from delta C. This has a value since it's a determinant, and its value is 4 times 2 minus 1 times minus 3. This is equal to 8 plus 3, which is 11. Go back to delta C and start again. This time, remove the y column of numbers and replace it with the constants. And that, of course, will be referred to as delta y. Delta y is therefore equal to 2, 5, replace the y column with 4, 1, and that's a determinant. And that has a value. And its value is 2 times 1 is 2, subtract 5 times 4, which is 20, for a total of minus 18. Now, the solution to the system is the following. X is the value of delta x over delta C. That's the solution for x. Delta x is 11, and delta C is 19. So x is equal to 11/19. Similarly, you could probably guess what I will do now, is for y must be delta y divided by delta C also. And delta y divided by delta C is minus 18 over 19. The solution to the system, therefore, is x comma y is equal to 11/19 comma negative 18 over 19. You can see why we write these solutions that we do algebraically in brackets is because there's a reference to a point on the graph. I have shown you how to classify systems using a graph and algebraically using ratios. I will now show you how to classify systems using determinants.